This is the first in a series of 3 videos in which we are going to introduce the concepts of work, energy and power. To begin with, let's consider the motion of a particle of mass m, which is being pulled across a smooth horizontal floor by a constant force F, which is inclined at θ degrees to the horizontal. What's more, we're going to suppose that when the motion starts, the particle has velocity u, that the motion lasts for time t seconds, and that at the end of this time the particle has moved s meters and has velocity v meters per second. Then, the mechanics that we have already done enables us to get an important relationship. First, if we apply Newton's second law to the right, the resultant force to the right is F cos theta, and that must equal the mass times the acceleration. Now, rearranging this, we get that the acceleration, A, is F cos theta divided by m. Since F is constant, and theta is constant, and m is certainly constant, we know that the acceleration is constant, so we can apply the constant acceleration equation, v squared equals u squared plus 2as. So, we've got v squared equals u squared plus 2 times f cos theta divided by m times by s. Or in other words, we've got multiplying by m and dividing by 2, we've got a half mv squared minus a half mu squared is equal to f cos theta times s. Now this equation is quite an important one, and we need to have a look at the terms in this equation quite carefully. So here's the equation again. We've got a half mv squared minus a half mu squared is equal to f cos theta times s. Now f cos theta times s is the work done by the force F when it is moved through a displacement of s, and it is calculated by finding the component of F in the direction of the displacement, that is F cos theta, multiplied by the displacement S. Now, on the left-hand side, we have half mv squared minus a half mu squared. You may well have met this already in some of your physics studies. It's the first time we've met it in our maths work. A half mv squared is the kinetic energy of a body of mass m which is moving with speed v. So a half mv squared is the final kinetic energy, and a half mu squared is the initial kinetic energy. So, the left-hand side gives us the change in kinetic energy during the motion, and the right-hand side gives us the work done by the force F during the motion. So, we've seen that the work done by a constant force F when it moves from A to B is the product of the component of the force in the direction A to B by the distance A to B. First of all, work is a scalar quantity. It doesn't have a direction attached to it. The unit of work is the joule. 1 joule is the work done when a force of 1 Newton moves 1 meter along its line of action. Now, in the case of the diagram that we've got here, if we've got the particle is moving from C to D, which is a movement of 5.6 meters, and one of the forces acting on the particle is this force P, which is at 7 newtons at 60 degrees to the horizontal, then the work done by P as the particle moves from C to D is the component of P in the direction C to D. Now the component of P horizontally is 7 cos 60 to the left. So the component of P in the direction C to D is minus 7 cos 60. So the work done by P as it moves from C to D is going to be minus 7 cos 60 times by 5.6, which gives us minus 19.6 joules. When the work done by a force is negative, we say that work has been done against the force. So we can say that the work done against P as the particle moves from C to D is 19.6 joules. So for our first example, we're going to try and find expressions for the work done by each of the forces in the diagram if the block moves distance s along the table. So, first of all, the work done by P is the component of P in the direction of motion, which is going to be P cos theta, times by the distance moved, which is s. So that's going to be P cos theta times s. In other words, PS cos theta. The work done by R is going to be the component of R in the direction of the motion, times by the distance moved. Now the component of R, well, R is perpendicular to the direction of motion, so the component of R in the direction of the motion is 0, so the work done by R is 0 times by s, which gives us 0. For the work done by W, well, that's the component of W in the direction of the motion, times by the distance moved, so that's times by s. But again, W is perpendicular to the motion, so the component of W in the direction of the motion is 0, so the work done by W is 0 times s, which is 0 again. And finally, the work done by F during the motion is the component of F in the direction of the motion, times by s. Now F is in the opposite direction to the motion, so the component of F in the direction of motion is minus F. So the work done by F is minus F times s, which is minus Fs. Or in other words, we have had to do work of Fs against the force F. Notice in this example that the work done by R and the work done by W was 0, and in general, if the force is perpendicular to the motion, then that particular force does no work. The second part of our first example, we've got to find the work done by each of the forces in the diagram as the block moves distance s up the plane. So, first of all, the work done by P is going to be the component of P up the plane times by s. The component of P up the plane is P cos beta, so the work done by P is going to be P cos beta times by s, or PS cos beta. The work done by R is 0 because R is perpendicular to the plane. r is perpendicular to the motion, so therefore the component of r in the direction of the motion is 0. So we've just got 0 times s, which gives us 0 for the work done by r. The work done by w is the component of w up the plane times by s. Now w has got a component of w sine alpha down the plane. So the component of w up the plane is minus w sine alpha. So the work done by w is minus w sine alpha times by s, which is minus ws sine alpha. And finally, the work done by f is the component of f in the direction of motion times by s. Now, f is in exactly the opposite direction to the direction of the motion, so the component of f in the direction of motion is minus f. So the work done by f is minus f times by s. For our second example, we have to find the work done against gravity by a shop assistant who lifts a box containing 6 bottles, each of weight 15 newtons, from the floor to a shelf which is 1.2 meters above the floor. And we need to state any assumptions made in answering the question. So, we've got the box is being lifted 1.2 meters upwards to go onto the shelf. So the work done by the weight is the component of the weight in the direction of the motion times by the distance that it's moved. So the component of the weight in the direction of the motion is minus 90 newtons times by the distance moved, which is 1.2. So the work done by the weight is minus 90 times by 1.2, which is minus 108 joules. So the work done against the weight, or the work done against gravity, is 108 joules. The assumption that we've made there is that the box and the bottles weigh 90 newtons. In other words, we're assuming that the box has no weight itself, or is negligible compared to the weight of the bottles. For example 3, we have a heavy box of mass 50 kilograms is pulled by a constant force of 120 newtons, inclined at 30 degrees to the horizontal along rough ground. We've got to find the work done by the force when the box moves 10 meters, and we also have to find the frictional force if we're told that the box has an acceleration of 0.8 meters per second squared. So here's our box, and we're moving it 10 meters along the ground. So our force diagram, well, we've got first of all the force of 120 newtons at 30 degrees to the horizontal. We've got the reaction from the ground on the box, we've got the weight of the box, and we've got the frictional force. So the work done by the force of 120 newtons is going to be the component of the 120 newtons in the direction of the motion times by 10, which is the distance moved. So the component of the force is 120 cos 30. So the work done is going to be 120 cos 30 times by 10, which gives us 1039 joules. If we're going to find the frictional force, we're going to need to use Newton's second law. So we know we've got an acceleration of 0.8 meters per second squared. Applying Newton's second law horizontally, we've got 120 cos 30, which is the component of the 120 newtons horizontally, minus F, must equal the mass times the acceleration, which is 50 times by 0.8. So we've got F is 120 cos 30, take away 40, which gives us 63.92 newtons. And the work done against the frictional force when the box moves 10 meters. Well, when the box moves 10 meters, the work done by F is the component of F in the direction of the motion, which is minus 63.92, times by the distance moved, which is 10. So the work done by F is minus 63.92 times 10, or minus 639 joules. So the work done against F is 639 joules. Example 4, we've got a car of mass 1.4 tons. Now remember, a ton is 1,000 kilograms. So we've got a car of mass 1.4 tons, travels at constant speed up a hill inclined at 8 degrees to the horizontal. We're to model the resistance to the motion of the car as a single constant force of 170 newtons. We have to find the total work done by the car as it travels 50 meters up the hill. Well, we need to start off with a good clear diagram. So we've got our car going up the hill. We've got the weight of the car is 1400 G. We've got the driving force produced by the engine of the car. We've got the normal reaction, and we've got the resistance forces of 170 newtons. Now, the work done by the car is the work done by the driving force. So one way of attacking this question is to use Newton's second law to find out what the driving force is, and then work out what the work done by the driving force is. So we know the car is moving up with constant speed, which means that there's no acceleration. So applying Newton's second law up the slope, we have d minus the component of w, or the component of the weight down the slope, which is 1400 G sine 8, minus the resistive forces of 170 newtons. The reaction force has no component up the slope, it's perpendicular to the slope. So our resultant force is d minus 1400 G sine 8 minus 170 must equal the mass times the acceleration, which is 1400 times 0, which is 0. So that tells me that d must be 2079.5 newtons. And the work done by the car is the work done by d, which is going to be the component of d in the direction of the motion, which is just d, times by the distance moved, which is 50. So the work done is 2079.5 times by 50, which is 104,000 joules, correct to 3 significant figures. Now at this stage, pause the video and have a go at these 3 questions. And when you finish the 3 questions, restart the video, because there's just a little bit more to come before we get to the end. Now we know that if a particle moves distance s in a straight line, when it's acted upon by a constant force of magnitude p newtons, acting in the same direction as the displacement, then the work done is P times S joules. Now, if we have a think about the graph showing how the force varies with the distance travelled by the particle, Well, because the force is constant, we're simply going to get a straight horizontal line for the graph. And if we think about the area underneath the graph between 0 and S, then that is precisely P times S. So the area underneath this force displacement graph gives us the work done by our constant force as it moves distance S in the direction of the force. Now there are going to be times when the force that we want to consider won't be constant. But if we've got a force then that isn't constant but is acting in the same direction as the displacement of the particle, then what we've done suggests that the area under the displacement force graph will give us the work done by the force. So in order to calculate the work done by the force, what we're going to have to do is integrate the relationship linking the force to the displacement between 0 and S. That will give me the area under the displacement force graph between 0 and S, which is precisely the work done by the force as the particle moves distance S in the direction of the force. Now we'll find this result is quite useful when we are thinking about the work done in stretching an elastic string or spring, which we will be doing later in this sequence of videos. So that ends our first look at work. The next video will be looking at the link between work and energy.